All right, everyone, ready for another deep dive? Today we're taking a closer look at something pretty amazing, something we all experience every day without even realizing it.
Oh, yeah. Definitely something we take for granted.
You got it, we're talking about Earth's magnetic field.
The invisible force field that surrounds our planet.
Exactly. And, it's not just about making compasses work.
Right. It's way more fundamental than that.
Yeah, and to really wrap our heads around it, we're turning to some seriously cool source material.
Oh, this is going to be fun.
So this website we found is called Open Educational Resources, Open Source Physics at Singapore.
I've heard of them. They're known for their interactive simulations, right?
Yeah, and they have this amazing one that lets you visualize how the Earth's magnetic field interacts with a simple bar magnet.
So we can actually see those invisible forces in action.
That's the idea. I mean, normally we just talk about the magnetic field, but this actually lets you play with it, see how it responds.
That's a great way to make these abstract concepts more tangible.
Right. And I have to admit, even though this site is designed for students, I kind of felt like a kid again, messing around with virtual magnets.
Who doesn't love playing with magnets?
Exactly. But on a more serious note, this stuff is crucial to understanding how our planet works on a fundamental level.
Absolutely. I mean, where do you even begin with something as vast as Earth's magnetic field?
Well, I guess it all starts at the heart of our planet, literally.
You mean the core?
You have the core.
Yeah.
It's this churning mass of molten iron constantly in motion.
Right, and that movement generates electric currents.
And those currents are what create the magnetic field that extends way beyond our atmosphere.
It's like Earth is this giant dynamo churning away and creating this protective bubble around us.
That's a great way to put it. We call it the magnetosphere. And it's essentially Earth's invisible armor against all that radiation bombarding us from space.
Yeah, without the magnetosphere, life on Earth wouldn't stand a chance.
Seriously, so we owe a lot to this invisible force field, huh?
Absolutely, but I think it's also mind-blowing how this whole thing works on such a massive scale.
Right. Like, how does that molten iron create a magnetic field that affects something as small as a compass needle?
It's all about those magnetic field lines.
Those invisible lines of force that connect the Earth's magnetic poles.
Exactly. And a compass needle is actually a tiny magnet itself.
Oh, I never thought of it that way.
Yeah, and because it's a magnet, it aligns itself with Earth's magnetic field lines, always pointing towards magnetic north.
So it's not just pointing north randomly. It's actually being drawn in by these invisible forces.
Exactly. And that's one of the things this simulation lets you see so clearly.
Right, you can actually visualize those magnetic field lines, both of the Earth and a bar magnet.
And you can see how they interact with each other, how they attract or repel depending on the orientation of the poles.
So cool. I mean, it really brings to life this idea that these forces are constantly at play all around us.
Definitely. And you can even manipulate the bar magnet in the simulation, see how the fields respond to each other.
Ugh, that's got to be fun to play around with.
It is. And it really helps you understand how magnetic forces work in general, not just in the context of Earth.
Okay, so it's educational and entertaining. I like it.
And I think it really drives home the point that these magnetic forces are everywhere, even if we can't see them.
Right. Like, have you ever stopped to think about how a compass actually works?
Before diving into this, not really.
It's like these invisible threads connecting the needle to the Earth's magnetic pole, guiding it.
And it's not just guiding compasses, it's protecting all life on Earth.
Right. Because without that magnetic field, we'd be fried by solar radiation.
The magnetosphere acts like a shield, deflecting those charged particles from the sun and keeping our atmosphere intact.
So it's not just about navigation, it's about survival.
It really is. And, this website has a bunch of other simulations, too.
Oh, yeah. Like what?
Well, there's one on Faraday's electromagnetic lab, which sounds pretty intriguing.
Ooh, that's a whole other rabbit hole we could dive into.
Yeah, but for now, I think we've got a pretty good grasp on the basics of Earth's magnetic field.
Definitely. We've established that it's generated by the movement of molten iron in the core. It creates this protective magnetosphere, and it's what makes compasses work.
And it's all thanks to those amazing magnetic field lines.
Invisible forces with a huge impact on our planet and our lives.
But thinking about Earth's magnetic field always makes me wonder about other planets.
Like, do they have magnetic fields too? And if so, are they as powerful as ours?
And what does that mean for the possibility of life on other planets?
Those are some good questions.
Questions for another deep dive, perhaps.
Definitely. We'll have to explore that next time. All right, so we've learned a lot about Earth's magnetic field, but It makes you wonder.
What about other planets? Do they have magnetic fields too?
Exactly. I mean, is this something unique to Earth, or is it more common in our solar system?
Well, it turns out not all planets are created equal when it comes to magnetism.
Really? So it's not a given that every planet has a magnetic field like ours.
Not necessarily. It all depends on a few key factors, especially what's going on deep down inside.
Oh, you mean the core?
Exactly. The composition of a planet's core and how active it is plays a huge role in determining whether it has a strong magnetic field or not.
So a planet with a more active, iron-rich core would have a stronger magnetic field, right?
You got it. Think of it like this. Earth's core is this massive churning dynamo of molten iron.
Creating those electric currents that generate the magnetic field.
Right. But other planets have different core compositions and levels of activity.
Okay, so give me an example. What about a planet like Mars?
Mars is a great example. It's much smaller than Earth, and its core has cooled and solidified significantly over time.
So it's not as active as Earth's core.
Nope. And as a result, Mars has a very weak magnetic field, almost negligible compared to ours.
So basically Mars is getting bombarded by solar wind.
Pretty much. A weak magnetic field means less protection from all that harmful radiation from the sun.
That doesn't sound very hospitable.
You're right. In fact, scientists believe that Mars's thin atmosphere is a direct result of its weak magnetic field.
So over billions of years, the solar wind basically stripped away a lot of Mars's atmosphere.
Yeah, it's a stark reminder of just how crucial our own magnetic field is for life on Earth.
Makes you appreciate our invisible shield even more, right?
Absolutely. But it also raises interesting questions about other types of planets.
Like what?
Well, we've talked about rocky planets like Earth and Mars, but what about the gas giants like Jupiter?
Oh yeah, they don't even have a solid core, do they?
Nope, gas giants are a different story altogether.
So how do they generate a magnetic field?
Well, instead of a solid core, they have a core composed mostly of metallic hydrogen under immense pressure.
Metallic hydrogen.
Yeah, it's wild. And it creates a magnetic field that's way more powerful than Earth's.
Seriously? How much more powerful are we talking?
Well, for example, Jupiter's magnetic field is so strong that it actually extends beyond the orbit of its moon Saturn.
Whoa, that's massive. I mean, that puts things into perspective.
Definitely. And it shows that the type of core a planet has directly impacts the strength of its magnetic field.
Which in turn affects its ability to hold onto an atmosphere and potentially support life.
Exactly. It's all interconnected.
So we've got Earth with its life-sustaining magnetic field, Mars with its weak field and a thin atmosphere, and Jupiter with its super strong magnetic field.
What a range. It makes you wonder.
If there's some kind of Goldilocks zone for planetary magnetic fields.
You mean just like there is for habitable zones around stars?
Yeah, like maybe there's a sweet spot for magnetic field strength that's ideal for life.
It's a fascinating thought, and it's something scientists are actively researching.
Well, it seems like there's still so much we don't know about planetary magnetic fields.
Definitely. But the more we learn, the more we realize how crucial they are for shaping planets and influencing their potential for life.
Makes me appreciate our own magnetic field even more.
Me too. It's not just some abstract concept, it's a fundamental factor in making Earth the habitable planet we know and love.
Okay, so we've covered the basics of how magnetic fields work on different planets. But, you know, it just occurred to me that we've been talking about these magnetic fields as if they're static.
Oh, you're right. We haven't even touched on the fact that magnetic fields can change over time.
Exactly. And I'm guessing that's especially true for Earth's magnetic field, since it's generated by this dynamic churning core.
You're on the right track. Earth's magnetic field is far from static. It's constantly shifting and fluctuating.
Seriously, like how much does it actually change? Is it something we would even notice?
Well, over very long periods, the changes can be quite dramatic.
Like, what do you mean by dramatic?
Well, how about this? Earth's magnetic poles have actually flipped multiple times throughout history.
Wait, what? You mean north becomes south and south becomes north?
Exactly. It's a phenomenon called geomagnetic reversal, and it happens because of complex changes in the flow of molten iron within Earth's core.
Okay, my mind is officially blown. How is that even possible? I mean, it seems like something out of a sci-fi movie.
I know, it sounds crazy, right? But the evidence is clear. These reversals have occurred many times in Earth's past.
So it's like our planet has a built-in reset button for its magnetic field.
In a way, yes. And, you know, the exact mechanisms behind these reversals are still being studied. But we know they're a natural part of Earth's history.
So how does this flipping actually happen? Like, Does it happen overnight, or is it a more gradual process?
It's definitely not an overnight thing. It's a gradual process that unfolds over thousands of years.
Thousands of years. Wow, that's a long time.
It is, and scientists can actually track these changes by studying the magnetic signatures preserved in rocks and sediments.
So it's like a geological record of Earth's magnetic history.
Yeah, it's pretty amazing. We can look back in time and see how the magnetic field has changed over millions of years.
That's incredible.
Yeah.
But it also makes me wonder, if these reversals have happened before, do we know when the next one might occur?
That's the million-dollar question. Scientists are actively monitoring the Earth's magnetic field, looking for clues about the next reversal.
So are we overdue for a flip?
It's hard to say for sure. There's evidence that the magnetic field is currently weakening, but that doesn't necessarily mean a flip is imminent.
And what would happen during a reversal? I mean, would we be in danger if the magnetic field weakens?
That's another area of active research. Some scientists believe that a weakened magnetic field during a reversal could make Earth more vulnerable to solar radiation.
So more of those charged particles could reach the surface.
Potentially, yes. And that could disrupt satellites, interfere with communication systems, and even cause power outages on the ground.
Wow, so it's not just a matter of updating our compasses. A geomagnetic reversal could have some serious consequences for our modern world.
It's definitely something to keep an eye on. But it's also important to remember that geomagnetic reversals are a natural part of Earth's history.
So life on Earth has survived these flips before.
Exactly. It's reassuring to know that our planet and the life it supports have weathered these magnetic storms in the past.
Well, that's somewhat comforting. But it also makes me realize just how much we still don't know about our own planet and the forces at play within it.
Absolutely. And that's what makes studying Earth's magnetic field so fascinating. There's always more to learn and discover.
Speaking of which, there's one more aspect of Earth's magnetic field I think we should explore.
Oh, what's that?
Its interaction with the solar wind.
Ah, yes, the solar wind. We've mentioned it a few times, but we haven't really delved into how it interacts with our magnetic field.
Right, and I'm guessing it's not just a positive breeze.
You're right about that. When the solar wind collides with Earth's magnetic field, things can get pretty spectacular.
Okay, so the solar wind and Earth's magnetic field, it sounds like a cosmic showdown is about to happen.
You could say that. It's not exactly a gentle breeze, this solar wind.
Oh, I'm starting to get that impression. It's not just some, cosmic dust blowing around, right?
Yeah. Right. It's a stream of charged particles constantly flowing out from the sun, and when those particles collide with Earth's magnetic field, well, that's when things get really interesting.
Okay, I'm all ears laid on me.
Ever seen the Northern Lights? Or the Southern Lights? Those incredible displays of color dancing across the night sky?
Oh, yeah. Absolutely breathtaking. I've always wanted to see them in person.
Well, guess what? Those auroras are a direct result of the solar wind interacting with Earth's magnetic field.
No way. Seriously. I always thought auroras were just some kind of atmospheric phenomenon.
It's actually particles from the sun. They get trapped by Earth's magnetic field lines and funneled towards the poles. And when those particles collide with atoms in the upper atmosphere...
They light up.
Exactly. They excite the atoms, causing them to emit light. And that's what creates those mesmerizing colors we see as the auroras.
So it's like a cosmic light show triggered by this invisible collision between solar particles and our atmosphere.
You got it. The solar wind basically paints the sky with these incredible displays of light.
Suddenly, the phrase solar wind seems way more exciting.
Right. But, besides creating these beautiful auroras, this interaction between the solar wind and Earth's magnetic field plays another very important role.
Oh, what's that?
It protects us.
Right, you mentioned that Earth's magnetic field acts as a shield against solar radiation, but I'm having a hard time picturing how that actually works.
Well, think of it this way. The solar wind is constantly trying to bombard Earth with all these charged particles.
Like an onslaught of tiny bullets.
Exactly. But our magnetic field acts as a barrier, deflecting most of them away from the surface.
So it's like our own personal force field, constantly pushing back against the solar wind.
A very good analogy.
But if it's this constant push and pull, does that mean our magnetic field could ever get overwhelmed?
That's a good question, and it can happen especially during events called solar storms.
Solar storms. Are those different from the regular solar wind?
Yeah, during a solar storm, the sun releases a much more intense burst of energy and charged particles.
So a supercharged version of the solar wind?
Exactly. And when one of those hits Earth, it can really put pressure on our magnetic field.
Like a cosmic tug of war.
Exactly. The sun's energy versus Earth's magnetic field.
And if the sun wins?
Well, in extreme cases, some of those charged particles can actually penetrate our magnetic defenses and reach the upper atmosphere.
It doesn't sound good.
It can cause some problems, it can disrupt satellites, interfere with communication systems, and even cause power outages on the ground.
Oh, wow. So those geomagnetic storms we hear about are basically battles between the sun and Earth's magnetic field.
Pretty much.
That's both incredible and a little bit scary, to be honest.
They can be powerful events, for sure, but they also highlight just how important our magnetic field is.
Yeah, not just for life itself, but for all our technology, too.
Exactly. It's a reminder that we're vulnerable to these space weather events, even with our magnetic shield.
It's pretty mind-blowing when you think about it. I mean, we started this deep dive talking about compasses, and now we're talking about cosmic battles and invisible shields protecting us from the sun.
It's been quite a journey, right?
Definitely. I feel like I have a whole new appreciation for Earth's magnetic field now. It's this dynamic, ever-changing force that plays such a vital role in our lives.
It's amazing, isn't it? This invisible force field constantly battling the solar wind, creating these incredible auroras, and ultimately making life on Earth possible.
It's a reminder that there's so much more to our planet than meets the eye.
And so much more to explore and discover. And who knows what future discoveries await us as we continue to study these fascinating phenomena.
Well said. I think we've covered a lot of ground in this deep dive, and I hope our listeners are feeling a little more magnetically charged themselves.
Me too. I always find it inspiring to delve into these mysteries of the universe.
It reminds us that we're part of something much bigger than ourselves, connected to these cosmic forces in ways we can't even imagine.
Exactly. And that's the beauty of science, always pushing the boundaries of our understanding and revealing the wonders of the world around us.
Well, on that note, we'll wrap up our exploration for today. But as always, keep those minds curious and never stop questioning the world around you.
Until next time.
Thanks for joining us.